Good morning, everybody. In this session, let us discuss about error minimization in instrument transformers. We have ratio error and phase angle error. So ratio error can be reduced by reducing the difference between Kn and R because it is defined by Kn minus R by R into 100. So if Kn is brought closer to R, error is minimized mathematically if you consider. So R is nothing but given by IC by IS. N plus IC by IS. So IC by IS, if it is small, so Kn will be equal to almost equal to R. So if IC by IS ratio must be small, the numerator IC must be as small as possible, or the ratio also must be small as possible, where IC is nothing but the core component of current. Similarly, if you consider phase angle error, it depends on magnetizing component of current. So let us see the different methods available for error minimization. First one is by handling the design aspect. So if we take up the materials offering low permeability, low hysteresis and eddy current losses for the core. Already you have studied about hysteresis loss, eddy current loss in your first year of engineering in basic electrical. So if we use such a material having low permeability, eddy current and hysteresis loss, core loss component current can be reduced. So while designing the core, we should see to that the joints are as minimum as possible. If the joints are minimum, reluctance can be reduced and hence IM also can be reduced. So both IC and IM can be reduced by suitably selecting the correct material at the same time by minimizing the joints. So by handling the design, we can minimize the errors, both ratio and phase angle errors, because ratio error is dependent on core component. Magnetizing component of current decides the phase angle error. Next method is use of shunts. So if we use shunts, we can reduce secondary current IS. In the secondary circuit, if we connect shunts, maximum current will be bypassed and hence IS gets reduced. Thereby, ratio error can be reduced. Third method is turns compensation. By reducing the secondary turns of CT, the ratio error can be minimized. So to understand this, let us take a simple example. Let us consider 1000 by 5 CT having core component of current 6 amperes, magnetizing component of current 4 amperes, and it has got 1 turn primary operating at full load. So for this case, R will be equal to N plus IC by IS. N is nothing but the turns ratio, which is 1000 divided by 5, which is 200. So 200 plus IC is 6, IS is 5. So 200 plus 6 by 5 will give us 201.2. And Kn again is nothing but transformation ratio 1000 by 5, 200. So if we calculate ratio error here, it will be 200 minus 201.2 by 201.2 into 100, which will give us minus 0.59%. Now, if we reduce the secondary turns by 1, our NS will not be 200, it will be 199. So turns ratio will now become NS by NP, which will be 199. Earlier, primary turn was 1, secondary turns were 200. Now secondary turns have been reduced by 1, it is 199. So ratio is now 199. Now we recalculate R, which will be 199 plus 6 by 5, which is 200.2. Kn remains as it is, 1000 divided by 5, which is 200. Now if we calculate the ratio error, it will give us minus 0.09%. So the ratio error has got reduced by reducing the secondary turns. And the last method is leakage reactance. So the leakage reactance between primary and secondary, generally by leakage flux, will increase the ratio error. Hence the windings can be arranged as close as possible to reduce the leakage reactance. So for that purpose, we can opt for ring type core or toroidal shape core of transformer, wherein the leakage reactance can be reduced. If that is reduced, the ratio error can be handled. So this finishes with error minimization in CT. So this concludes this particular session.